Let's talk about electropneumatics. Electropneumatics are just pure pneumatic systems where we have pilot information or pilot air going in as our information to activate our cylinder either one way or control the DCV or even to control a valve. We can, we could get any kind of valve with a pilot on it. So what I want to do is I want to talk about how we actually make all of that happen with just electropneumatics. So what's going on is that when we have a DCV or a valve, some activation makes it move. Okay, so my valve is going to change its state somehow. So we've discussed pilots, we've discussed rollers for limit valves, we've discussed push buttons, we've discussed a whole bunch of things that can activate a valve. What I want to do is I want to add solenoids. It's pretty cool. So I'm going to talk about some components that are called solenoids, and actually we're going to put them in valves, and actually we're going to call them solenoid valves. The other thing is that I want to talk about other electrical components that we use in electropneumatics. Now, as you know, when you're taking a look at any kind of purely pneumatic system, you guys are used to limit valves. What we're going to do is talk about limit switches. Yeah, so this is a cool old limit switch. And it's a big thing, and what it's going to do is when a cylinder is going to come out, it's going to hit it, and you can hear it clicking. So it's going to indicate that something has reached its limit. I can put this on the inside of the cylinder or the outside of the cylinder, so I can have my cylinder coming in or out. I'll just get this guy. So essentially what's going to happen is I can actually put this on the inside, and if I had like a head on my cylinder and this was here, and then this retracted, it would press onto it, and it would close it, and I would get a signal from this. Depending on if it's a normally open or a normally closed, I'm still going to get a signal. We can say that if it's a normally open, it's going to close and give us a high signal. If it's a normally closed, and then I hit it, and it changes state, it'll become open. So actually we get a low signal. So however you look at it, I can get information from purely pneumatic systems with a limit valve, which then gives me a burst of air, and I can do something with that. Or I can use a limit switch, and then I can do something with the electrical current or electrical potential that comes out of this. So I did mention something about solenoids. What's a solenoid? Well, I'm going to introduce a solenoid to you. Very cool things. And I'm also going to use a little tiny limit switch. So I've got a small limit switch hooked up to this solenoid, and I've got a small lead acid 12-volt battery. And what I'm going to do here is I'm going to close this. And this guy is just an electromagnet, and this is a plunger. So this is the basic solenoid. It's just all this is a solenoid. It doesn't control a valve. Ready? Here we go. Cool, eh? Yeah. So that moved. Yeah, it moves a little slower. See how far I can push that out. Can I go even there? Yeah, a little bit. It needs to go in here. It's not designed to be that far out. So this thing is actually going to apply a lot of force if I have it small like this. So what's going to happen is that this guy can be used to change the state of a valve. I've got a solenoid valve here. So what's going on is you can see this is a big coil in here. This is a really powerful thing. So there's some kind of activation in here, or a spool of some type that's going to move. It's going to change the state of this valve. So that's a pretty heavy kind of solenoid valve, and that has an exhaust that's actually coming out here. So this is a 3-2 valve. And there we go. This is a much larger, more typical pneumatic solenoid valve. And this guy this is also a 3-2. So it's got one, that's my in. These are my two outs, port 4 or port 2 and port 4. And then there are two exhausts in here as well. So what this is, it's a spring return valve. So we know that when we looked at pure pneumatic systems, we had springs that actually activated the spool or changed the state of the spool inside the valve, and we also had pilots and mechanical things, push buttons and stuff. In this case, I've got a spring on one side. On the other side, I've got a solenoid. Yeah, I've got one of these. It's actually physically pushing the spool inside. Now, let me go over to here. This is also a similar valve. This is a little tiny valve, actually. This is considered mini-matics. Yeah, little small pneumatics. This is from a company called Clippard, and I use these for my medical devices. So that's also a little solenoid valve. That's pretty cool. And I've got another solenoid valve in here, and you can see all of these have a kind of a common thing. They've got a coil on them. They've got a solenoid in them. And here's a little tiny guy. Little tiny guy. I do not have a double acting solenoid valve. So I will give you the proper name of this. This is a 5-port DCV, but it is a solenoid spring return DCV. It has one solenoid and one spring. The other thing is if this had two, I could go and order one of these that actually has two solenoids on it, and that would be a double solenoid DCV or a double solenoid 5-2 valve. You can also get a double solenoid 5-3 valve if you want. So however that works, it's okay. I think you guys get it, that there's this little thing in here that's electromagnet and it makes something move when we give an electrical impulse. Often we get the electrical impulses from limit switches. You know, I can also get an electrical impulse from a relay. I could have this little relay here, actually, you know, part of maybe a logic circuit where a couple relays are maybe making some logical decisions. And then this relay finally says, hey, okay, solenoid, actually go ahead and energize. Yeah, that's a word we use for solenoids. And that solenoid obviously would be in some kind of valve because we're actually controlling air, right? Because we're studying pneumatics or electropneumatics. So also maybe this particular relay is going to reverse logic for us. Actually, this is kind of really important point because often what we do is we have a limit switch that's normally opened, but we may actually need to, when it activates something, we want to terminate something. Yeah. So if this thing becomes activated, which means it's a closed switch, and I want to turn something off, what do I do? Yeah, I can reverse the logic with a relay. Relays are so cool. So anyway, so relays, all of this cool stuff. Let's put all this together and actually study some of the symbology and actually kind of look at some examples of electropneumatics. So here we go. So we've got a solenoid in electropneumatics. That is the symbol for a solenoid. So what we're looking at is it's essentially an electromechanical device. So the mechanical device may be as simple as an electrical contact or a relay. Oh yeah, you know what? This relay, it's actually got a little solenoid in it, but we don't call it a solenoid. It's actually just an electromagnet, but it's making something move. So essentially, when we have an electromagnet that makes something move, that's a solenoid. So in electropneumatics, solenoids are used to move spools, and there's some symbols here. So that's actually the symbol for a solenoid valve, or pardon me, that's a symbol for a solenoid on a valve. In this case, this is exactly like this. Actually, that's this second example, the one on the right, is exactly like this because that second one is a 5-2 DCV valve. So I've got a solenoid on one side and a spring on the other. Now, actually, I can have a solenoid that, I can have a valve that, again, has two solenoids, one on either side. So different symbology, pardon me, that's the symbol for a solenoid on a valve. A solenoid may refer to a type of transducer that actually takes some kind of electrical impulse and turns it into motion. But pretty much that's what a solenoid is. Again, like, you know, in a relay, there's motion going on there. That's pretty much a solenoid in there. Anyway, you can click on here and go in here and see what Wikipedia says about a solenoid. There's a lot more information on there. But specifically in electropneumatics, I want to stick to that. I want to give you an example here of, you know, how we actually, what actually happens in a valve and what's going on with the cylinders and stuff like that. So in this case, if this solenoid is off, so it's not energized. That's the term we use. We either energize it or we de-energize it. It can also, I guess, be said that it's just off. So what we have here is we have a solenoid and it is not energized. So this valve is in its normal state. Actually, the reason it has a normal state is because it has a spring on it. It's interesting. What if it didn't have a normal state? That's a good question. Okay, let's continue on. So this guy's got a normal state. If I do not energize this is valve in its normal state. I've got my pressurized air coming up here, and essentially my cylinder is in retraction. No matter what, it's just in retraction all the time. There's no way I can pull that out. It's in retraction. There's pressurized air pushing it in retraction the whole time. If I want to extend, well, we know what we do with the valve. We just activate the valve. So in this case, we're just going to send an electrical impulse, and we're going to energize the solenoid. Yeah, so it moves the spool and all of a sudden air goes from 1 to 4 and the cylinder starts to extend. I think this is just all really simple, and that's exactly what's going in here. When we energize this guy, then what we're doing is actually we're doing a 1-4 action, right? So the action in this case is 1-4. So the activation number in this case is 1, 4. So the air goes from 1 into 4 and the cylinder extends. I think we're good with that, okay? So now this is the symbology here that we need to get used to. That's pretty close to a limit valve, but it's a little bit different. We can see that that is, there's a switch in there. It's actually a normally open switch. I'm going to show you what a normally closed switch looks like. It's not complicated. So what's going on is that that is a limit switch and not a limit valve. I need you to start to get used to saying switch and valve and understanding that they are completely different things. Although they both give us some kind of pulse or electrical or mechanical or air pulse that we can, you know, that's a piece of information actually that's coming at us that says, oh, something's reached its limit and we can do something with that. Now, that's actually an electropneumatic device, right? We actually see that in the circuits. This is actually, where we go. I don't have a limit valve anywhere. So let's just, a limit switch, pardon me. No, I've got a limit switch here. Sorry, I have a limit switch. Okay, so here's my limit switch, okay? That's giving me an electrical impulse. It's translating an event into an electrical impulse because that's what switches or sensors do. In this case, that's a switch. Okay, good. So the other thing is that what does it look like in the actual control circuit? You know, the ladder circuit. There's actually a symbol for that. It's a separate symbol for that. Later on in a different lecture, we're going to like go deep into all kinds of symbols that we see in ladder logic for electropneumatics. But right now, we'll just stick to the two kinds of things we need to talk about. One is the actual electropneumatic device that's actually in the circuit, which is this limit switch, and that's the symbol for it. And the other, oh yeah, and it's a spring. Oh yeah, it's a spring in it. It's got a normal state, right? And the other is the limit switch that we see in the ladder logic, and that's what that symbol looks like. So that's a normally open limit switch, yeah, because it looks open. We'll get into all the other kinds of limit switches later. For now, let's continue. Okay, good. Here, so limit switches examples. Limit switches are used to translate an event, right? All different kinds of events. We could talk about like just a door opening all the way, and the limit switch is going to tell me, okay, that door's opened all the way. Or another limit switch saying the door is closed all the way. So there are lots of kinds of limit switches. Actually, they're really cool limit switches. One is actually called a reed switch. Let's not talk about that. Let's go on and talk about maybe some other examples, essentially. Essentially, what's going on, even a drawer, like a drawer opening all the way or closing all the way, any physical thing, any event that's actually making something go and it has a limit. Well, let's stick to electropneumatics. Yeah, in electropneumatics, switches are used to indicate that a cylinder, wait a second, has reached its limit. Now, wait a second. Does that mean, okay, that's the retraction limit. Okay, so I'm going to put that here. What about this? Does it have to go all the way up there? Do I have to put my limit switch right here? Well, no. If my cylinder actually reached, if I wanted to show that my cylinder is kind of like on its way out, I can actually put this here. Right? That's not a problem. You can actually put the limit switch anywhere. Does it actually indicate a limit? Or maybe it does. Not the limit of this, the limitation limit of this, but whatever limit you want. Say, well, this is my limit here. So when it gets to this point, right, that's my limit. So it's reached the limit. So there you go. That's the term limit, and that's how we use it. So mostly we can say that it wants to tell it, a limit switch tells us that a cylinder's reached its outermost or innermost location, but we don't specifically have to have those locations telling us that that's what's going on. So we don't have to say it's fully extended or fully retracted, but hey, oh, there's like a whole kind of thing here. This is an electropneumatic diagram. So it's not a ladder diagram that's electropneumatic. That's the control for this, but this is an electropneumatic diagram. And what we have is we have a cylinder and a DCV, nice and simple. It's not complicated. We're used to that. And we can see we have some new symbols in here. One is the solenoid that's actually going to move the spool instead of a pilot or a push button or something. And the other is that we're not using limit valves anymore. Yeah. So limit switches. And that, oh, look at that. What's that? Yeah. That's a normally closed limit switch. Okay, so you can go buy normally closed limit switches or normally open limit switches. Why would you want a normally closed limit switch? It depends on the application and the type of logic. This doesn't tell us what it's about, but this is an example here. So there are some symbols and electropneumatic symbols that we can get used to. Now let's actually get into some ladder logic and add ladder logic. Okay, what's going on here is that I have two solenoid valves. Okay, I've got two solenoid valves. I know that if I energize one solenoid valve, the spool is going to move. The valve is going to change. The activation is going to change. So if I did solenoid A plus, my activation number is going to be 1, 4. We can see that. So air is going to go from port 1 to port 4, and it's going to make the cylinder extend. Easy. We also know that when that happens, air is going to go from port 2 to port 3. But let's continue with solenoid B minus. So when solenoid B minus is energized, it moves the spool. Now it's the activation number in that case, or the activation number for that solenoid is going to be a 1, 2. So we know air goes from port 1 to port 2, and the cylinder retracts, and the air coming out of the cylinder is going to go from port 4 out to port 5, and it's going to go to exhaust. Okay, good. So now that's fine and dandy, and we see that we have some limit switches here. We have an outside and inside limit switch. What's going on is that, actually, you know what? If we take a look at this, this is cool. I'm gonna leave this mistake in here because it's interesting. It helps us highlight this. If you take a look at this, that's a normally closed limit switch. I just grabbed this image from this and I put it down here. But you know what? I should actually use a normally open limit switch here. And the reason is because, well, let's take a look at the logic. What would actually happen if I used a normally closed limit switch here? Well, this circuit, I don't think it would work properly. Let's take a look at it. So the ladder logic shows us what is actually going to happen with our electropneumatic circuit. In this case, if I press the start button, solenoid A plus is going to energize. Okay, well, just stop everything. Just don't do anything. Limit switch A. Okay, well, I've drawn it as a normally open in my ladder logic, but in my electropneumatic, I've actually drawn it as a normally closed. So, you know, that's an error. That I'm leaving it in here. Actually, I didn't mean to put it in here, but I mean, you know, I left it in there because I'm leaving it in because I think it's important that we highlight that you can't do that. So there's some incongruency in this diagram. This indicates that it's a normally open limit valve, and this indicates that it's normally closed. So let's just pretend this shows a normally open, then we can move forward. Okay, good. So, by the way, if this was a normally closed, nothing would happen. Actually, let's talk about that too. Let's actually make this guy a normally closed and see what happens. Now, if this was a normally closed, the cylinder, let's say the cylinder is at home. Okay, so we have to have a starting position. Actually, are there any springs here? Well, there's springs in the switches, but there's no springs in the valve. So this cylinder and that valve doesn't have a normal state. This cylinder could be extended or retracted. If it's extended, there's really no conflict here. Everything's going to be okay. Nothing's actually happening. But the fact is that it's actually not going to retract. The thing is, when I press the button, I want this to go out and then come back automatically. But the thing is, let's just leave it again with this error, okay? But let's just say this is normally closed. And I press the start button. What's going to happen? Nothing. Actually, nothing. The reason is because when it is retracted, because that is a normally closed valve, limit switch, what's going to happen is that the outside limit switch A plus, is actually going to be closed. So therefore, it's going to be energizing A minus. A minus is being energized. Okay, well, what happens if I press the start? You know what? Solenoid A does actually energize, but it doesn't win. Yeah, so if you don't have a double solenoid valve, let's just pretend. Yeah, we can do that. So see this double solenoid valve here? See this solenoid over here? Yeah, okay. So if I energize this solenoid, if I energize this one, it won't move the spool. It won't fight back this solenoid. It won't win. It'll stay in the position that this solenoid put it when we energized it. And as long as it's still energized. Okay, so it's same with pilots. If you have one pilot activated and the other pilot, you activate that pilot, it's not going to win unless you kick up the pressure or something. I'm not going to kick up the voltage. These things are designed for a particular voltage, so I'm not going to do that. So my problem here is that this ladder logic won't work if that's normally closed. So we have to think very carefully about which kinds of switches we put in here. Let's move on. Okay, so now this is a normally open limit switch. That's a normally open limit switch. What's going to happen is when I press the button, that button is going to energize solenoid A+. It's going to move the spool, and then air is going to come out of port 1 and go into port 4, and then the cylinder is going to extend. When it extends, it's going to press the limit switch A+. A+ is then going to become closed. It's going to energize. Now, wait a second. It's going to energize A-, but is that okay? Is there a battle going on? Well, no. As long as I'm not holding my finger on the start button, everything's okay. If you actually press it and hold your finger on the start button, it's going to go out and it's just going to sit there. It's actually not that good because you have two solenoids kind of fighting each other. You don't want that to happen. So you press, you let go, and what it does is that momentary signal shifts the spool. I don't need to hold that momentary signal to make the cylinder still extend, because the cylinder is not extending because the solenoid is pushing it. It's not happening. The cylinder is extending because the air is pushing it. The air is pushing it because the solenoid changed the state of the valve. That's it. The solenoid changed the state of the valve. So the state of the valve has changed. There's no spring in it, so it just stays that way. Okay, good. So we know the cylinder is going to extend. When it gets to full extension, or more specifically, when it hits limit switch A+, it's going to energize solenoid A-, and that's going to change the spool back to the other position, which is going to make the valve a 1-2 activation, and the cylinder is going to retract. So I think that makes sense. Now, I did say that when I press the button, I can release it because that spool just moved. I mean, it doesn't have a normal state, so it changed the state of the valve. That's fine. I don't have to keep telling it to change the state of the valve. But what happens if I do? Take a look at this. What I've got is a single solenoid DCV. Okay, so that spring is always pushing on the spool. The spring is always pushing on the spool, and I happen to have one of those right here. Okay, so what's going on is that I can be guaranteed, if I do not energize this guy right here, depending on the configuration, I'll pretend that this configuration is exactly like we have here in this diagram. So this is a 1-2 activation when the spring is activated. So when this spring is activated, this is a 1-2. If I want to make it a 1-4, I have to energize this. That's fine. But if I want to keep it a 1-4, I have to keep that energized. If I let go, or if I de-energize this, it goes right back to a 1-2. So what's happening here is that if I want to do the exact same thing as we did in the last diagram, press a button, release the button, it goes out, it continues to go out, gets to the end, it retracts. We need a holding circuit. Yeah. The reason we need a holding circuit is because there's a spring in this valve that's always going to put it into a 1-2 state, and it's always going to retract my cylinder. If I want my cylinder to continue to extend, the signal that tells this guy to energize has to remain during the entire stroke until it gets all the way out to limit switch 2, or limit switch A+. So I think that makes sense. So you're going to see that whenever you're using a DCV with a spring in it, you're going to have to keep this guy energized as long as you want that cylinder to extend. Now, you might think about design as well. Let's say I wanted to have the normal state of a cylinder to be extended all the time. Just, you know, whatever. Or maybe I wanted to have a cylinder maybe extended for like a long time, for like an hour or maybe a day or longer. And then some other times I want to have the cylinder retracted and staying that way as well. I mean, I don't know, you think of the application. But what I'm saying is we have to think about the valve. Now, let's just say I wanted my cylinder to generally retract or extend whenever I'm not using it. Well, I'm not going to make it so I have to keep this guy energized the whole time to have it either extend all the time normally or retract all the time normally. I said normally, didn't I? Yeah. Usually when we say normally anything, what's going on is that if normally anything, we've got a spring in it. So what's going to happen is if there's a normal state to your cylinder, you want to hook your cylinder up to your DCV so that the spring activates it and it puts it in the normal state. Because if I hooked my cylinder up like this, it may actually retract or extend normally. And if I hooked it up like this, it would either retract or extend normally. So, you know what, we can hook up the, well, a cylinder has polarity, right? You guys know that. So, yeah, you got to think about all these things. Anyway, that's good for now. What we're going to do is we're going to jump into electropneumatics a lot deeper than this and a lot more of this ladder logic and more logical thinking. And we're going to get into a lot more symbology about limit switches and stuff like that. So I think that's all I have to say. Yeah, that's it. Okay, bye.